So this is the MOSFET VI characteristics, so often known as the drain characteristics. Actually, each characteristic curve displays the variation of drain current with the drain to source voltage VDS for fixed gate to source voltage. Suppose for a given positive VGS, okay, that VGS must be exceeding the threshold voltage, the drain voltage is made slightly positive with respect to the source. Current flows from the source to drain through the conducting channel. This channel is actually acting as a resistance, so that drain current ID is proportional to the drain to source voltage VDS. This gives the linear region or the ohmic region where the constant resistance is given. The net voltage drop between the gate and the substrate at the drain end and the net voltage drop at the gate to substrate at the source end, they actually differs. That can be observed in the physical dimension. Consequently, this thickness of the channel actually gradually decreases from the source to the drain. Okay, so thereby increasing the value of VDS, this effect is becoming more prominent. As a result, the channel resistance is increasing with the increase of VDS voltage, and then the drain characteristics is becoming basically bent towards a horizontal line. So this actually indicates a higher resistance, almost all infinite range. Okay, so when the VDS attains a value which is difference between VGS minus VDS, that is VT, the channel thickness at the drain end, okay, goes to almost zero, and this particular phenomena is known as the pinch off condition or pinch off point. At this point, a pinch off point, the drain current saturates at the value of ID set. Okay, so you can see here these are the different points where the ID set is starting. So these are called the pinch off region for different values of VGS. Okay, as and when the VDS is increased further, the pinch off points in the physical dimension, it moves towards the source, but the drain current remains constant. Okay, and this is why it is known as the saturation region or the active region of the drain characteristics. Okay, you can see here the saturation or the active current region. Note here, ID slightly increases with the VDS. It is not actually exactly horizontal line. Okay, in case of the JFET, we would have been seen like that. So this is called the channel length modulation. So there is a phenomenon called channel length modulation, for which instead of these lines not going for straight, okay, so it is going somewhat like this, okay, somewhat increasing. So this is due to the effect of what is called the channel length modulation. Okay, next slide will be showing the structure of n-channel depletion MOSFET. This is the slide is showing n-channel depletion type MOSFET. Note here is a layer of prefabricated n-channel at this point. Just below the gate, you have the layer of prefabricated n-channel. Okay, that's what the difference in between the enhancement mode MOSFET and the depletion mode MOSFET. So in depletion case, there will be a prefabricated n-channel in between the source and drain. Okay, that means channel is already established at this point. So that means the transition is on condition. Okay, what we can do, we can apply a certain voltage, obviously negative voltage, you can see, so that this channel can be removed from below the gate. Okay, So if you can remove this channel, prefabricated channel, by applying certain voltage, then the MOSFET becoming switched off. That means there will be no path or high resistance path in between source to drain. So that's what the depletion MOSFET. But mostly we will be using the enhancement type MOSFETs, where positive gate voltage will attract the channel and establish the channel or enhance the channel so that the source and drain terminal can be get switched on. So in case if you are applying certain positive gate voltage at this point, what will happen to this channel, prefabricated channel? It will only widens. That means the channel will be more established. Okay, so to make this off, what you have to do, you have to apply some negative voltage. Okay, increasing the drain voltage. Okay, when the channel is already present, increasing the drain voltage, it will attract the charge carriers from source to drain. Okay, and huge amount of current can be flowing. VDS at which the channel is pinched off and drain current stop rising, that is already we have mentioned, that is known as the pinch off voltage or saturation voltage. So at pinch off voltage, the drain current which is flowing there, that is known as the saturation current. Now to increase the saturation current further, the VGS can be increased, but obviously this is a one device, so you need to put it off by applying the negative voltage at the gate terminal. Okay, so next slide, we have just given this description for the N-channel depletion MOSFET. Now regarding the voltage transfer characteristics of the depletion type MOSFET, what you will find that this is the typical characteristics of the N-channel depletion MOSFET VI characteristics. So okay, as you can see from these characteristics, when VGS was just 0.5 or VGS equals 0 volt, so there will be a huge amount of current flow. Okay, whereas if we apply a VGS of minus 0.5 volt or minus a VGS that is 1 volt, minus a VGS that is 2 volt, that means VGS equals minus 2 volt, then you will find the currents are getting decreased. Okay, and if we apply certain voltage, VGS equals minus 4 volt, let's say, then you will find the device is entering into the cutoff mode. Okay, in mathematical equation, we can describe this behavior of the drain VI characteristics. So here are the list of it is given for the both the PMOS and NMOS. So let's concentrate on only the NMOS. Okay, so in case of the NMOS, if the gate voltage is less than the threshold voltage, it is in the cutoff mode of operation. In that case, ID is almost equal to 0. In case of VGS, that is the gate voltage is larger than the threshold voltage, higher than threshold voltage, and here at this condition VDS, the drain voltage, which is somewhat low, that means comparable to the gate voltage minus the threshold voltage. Okay, in that case in MOS, this current equation is given by Kn, that is the constant for the NMOS, and 2 Kn by 2 VGS minus VTH into VDS minus VDS whole square. Okay, that's what the equation for the linear region. And equation for the saturation region, just considering the channel length modulation, we are getting the equation for the NMOS this way. Similar for the PMOS, you can get, only thing is that for the PMOS, the gate voltage should be in the negative form. So the absolute value of the gate voltage, if it is less than the absolute value of the threshold voltage, okay, both are negative, so that is called the ID equals 0. That's the cutoff voltage. For example, the VGS is, let's say, minus 2 volt. Okay, whereas the VTH equals to minus 2.5 volt. So if as long as minus 2 is less than minus 2.5, in the negative axis you can just imagine. So ID will be 0. So when the magnitude of the gate voltage is exceeding the threshold voltage, in that case it is entering into the linear region and then further to the saturation region. Okay, so next few slides that will be giving you the concept of PMOS.